Okay, we're going to kind of continue on a little bit here, a little bit more with some organic. We'll look at a couple more examples of naming. That way, you know, when you go off to your organic venture in Chem 80, you'll learn it all again. All right, hopefully. All right, so obviously we talked about organic chemistry earlier on today. Remember, obviously, it is the basis of all organic molecules is the carbon-to-carbon bond with our hydrogens. We talked about functional groups, and remember that really the functional groups are the part of the organic compound that makes it a certain class of compounds. And those functional groups usually will sort of replace hydrogens in a alkane. And they can't give them some extra sort of functionality, if you will, like we talked about. You know, if you have like an OH group, you now kind of bring into play some solubility with water. You also bring into play also higher boiling points because it does have the ability to hydrogen bond with itself. Than say an alkane, which has a very low boiling point, low melting points. You know, again, for something like the difference between these two guys, if I can see it there we go. And again, even though they both do really contain 2 carbons, this being an alkane versus this being an alcohol, this guy, again, the alkane pretty much will have very low boiling points and melting points because it is going to use primarily dispersion forces, which are those very weak intermolecular forces we talked about. Alcohols, though, here will typically have very high boiling points and melting points, and that is because it does have the ability to hydrogen bond, and it will use that ability very well in the case of something like ethanol to do that. In fact, in terms of organic compounds, pretty much your alcohols are your champions in terms of boiling points and melting points. The only one that really sort of beats it out is the carboxylic acid that we saw in terms of a functional group. And that is because in a carboxylic acid, it's got a double polar situation going on here and here. It's got both of those groups, which means when 2 carboxylic acids get together, which is what happens, obviously, when they're trying to go, say, from liquid to gas and they want to break apart, they could do a lot of hydrogen bonding with themselves here. Again, the negative part and the positive part, these guys can bond. The hydrogen here and the oxygen there can bond, so they really bond very tightly with each other. And really, carboxylic acids have the highest, one of the highest in terms of organic chemistry compounds in terms of boiling points and melting points, because they actually can create a dimer. They can kind of do double hydrogen bonding within themselves, which makes it even a sort of stronger bond. The functional groups, again, are important to know. And as I mentioned before, you do need to know the different functional groups and what they mean. We talked about alkanes, and we talked also about hybridization like sp, sp2, sp3. That's basically your carbon-carbon single bond. That's your carbon-carbon double bond, and that's your carbon-carbon triple bond. Again, the difference in the geometries here, right? Tetrahedral to our trigonal planar, our triangular to our linear in terms of our geometries that are happening for each of those guys. We talked about sort of isomers as well. Isomers are guys that have the same formula, but different connectivity. And along with that, we really kind of jumped ahead there and talked a little bit about how to go about naming. And pretty much all naming, as I mentioned, really does fall back to the alkanes, are a good majority of it. And we always are looking for the longest carbon chain. Now we're sort of focusing just on alkanes here, but typically speaking, you're always looking for the longest continuous carbon chain. For example, if you had something like the alcohol here, you want the longest continuous carbon chain that contains the functional group. So typically that is what you're looking for when you're counting the longest continuous carbon chain. If it's something other than an alkane, it has some type of functional group like an OH, a carbon oxygen double bond, you want the longest continuous carbon chain that contains the actual functional group as part of it. And that will be the basis of the name, will be one of those alkane names. As we talked about as well, there are groups which are referred to as alkyl groups, which are really like our alkanes, but they're missing a hydrogen to allow them to bond in. So again, something like a CH3 group, there is a methyl group, and again, it's based off of methane. We talked about some different formulas. That is our expanded structural formula. Again, our condensed formula is something like this. And we also have line structure, which pretty much are just lines. You don't put anything else there. And as we talked about, if you have just a line with nothing there, that is a methyl group. If you have a line and they want something there, they will write something at the end of the line there that is not a carbon. Otherwise, you should always assume at the end of the line it's a carbon, and also obviously a carbon where they always come together as well will be carbons, right? In each of those cases. Any questions on any of that stuff there we talked about earlier today? Fun here. All right, so officially, as we talked about, we usually, as I mentioned in organic chemistry, there is a lot of names for the same thing. But usually in most cases, the IUPAC name is sort of the standardized name, sort of the official name that most people will sort of name. And there are, as I sort of demonstrated, I think with the ethane, there are different things that you do depending on the functional group that's present to the names. But a lot of them always comes back to the longest carbon chain and those alkane names. So the parent part of the name is the one with the longest continuous carbon chain. And again, it is not always the straightest. So you may be able to kind of go straight. You may have to go up and over or something like that when you're counting carbons. Once again, the only thing that you cannot do is kind of go up, over, and then decide to backtrack and come back around or anything like that and go around in a circle and do all those things. So you can't do those things. You basically have to go from one end to the other till you kind of hit a dead end, and then you got to count how many carbons there are. You do usually want to make sure that you kind of check all of it, all the possible options, because you may be surprised that, oh, there's like a longer carbon chain kind of hanging out there in a different direction. Once you do so, in most cases, again, it will be the base of the name, and that pretty much is going to be one of those alkane names. Anybody that is not part of that longest carbon chain, as we talked about, will be a group. And if it's a carbon-based group, it will be an alkyl group where you just put YL at the end of it. It'll have one less hydrogen than the alkane. If it's a halogen, like we used before, fluoro, chloro, bromo, iodo for iodine. And again, there are some special names of the groups along the way. We also always want to number the longest carbon chain. And the goal of numbering in the case of alkanes is to get the groups that are attached to the smallest numbering. So whichever way you need to go, left to right, up to down, that gets the groups that are attached to the smallest numbers. That is what takes priority in alkanes. As you move away from alkanes to things like double bonds, triple bonds, alcohols, other functional groups, when you do go to number, the priority shifts to those functional groups. So if you had an alcohol, you would want to number whichever way would give the alcohol the smaller number. So for example, if I had something like this, put some hydrogens in there. So I know this is an alcohol because it has an OH group. I would still do the same thing, count the longest carbon chain, which in this case is 1, 2, 3, 4, 5 carbons. 5 carbons is based off of pentane. Since this is an alcohol, it ends in OL, pentane becomes pentanol, OL. And in this particular case, we want a number to give the OH group the smallest number that's attached. which in this case would be, if we went this way, 1, 2, 3, 4, 5, as opposed to if you went right to left, 1, 2, 3, 4, and 5. So going left to right in this case gives the OH group the smaller number. And also something that occurs with a lot of functional groups is you also have to give the location of where the actual functional group is located. So this would actually be known as 2-pentanol, the 2 indicating that the alcohol group is located at carbon number 2. And that is because you could have the alcohol group moved over 1 carbon, and then it would be 3-pentanol, which would be something different. So in a lot of cases, if you got 3 or more carbons and some type of functional group like a double bond, triple bond, you do that with those as well. You do give the location of where those things are located. Now, for example, if we lock that into place for the alcohol and we had something else attached, say like this. Say we had a chlorine, for example, there. Because we would look at this here, this would still be our pentanol as an example. And between these two things that are attached, because this is the functional group, it would get the priority, which means we would obviously number the way we just talked about. And that means that this would be 2-pentanol. And because we have to number that way for the alcohol group, that means our chlorine is going to be actually at carbon number 4. And this would be 4-chloral 2-pentanol in that particular case. So once you sort of lock in the numbering of the longest carbon chain based on the functional group, then pretty much everybody else that's there has to obviously be numbered accordingly. You don't start renumbering for other things that are there. You basically just keep the numbering. So outside of alkanes, basically it's the functional group that takes the priority. Alkanes, it is actually the groups that take the priority. So you always want to number whichever way makes more sense for the groups. But past that, it's really the functional groups that actually do take the priority. And we also do that, by the way, with things like a double bond here, for example. This would be 1, 2, 3, and 4 carbons, which is based off of butane. Because it does have a double bond, it is an alkene, ENE. So butane becomes butene, ENE. And we do need to give the location of that double bond, which in this case, we go right to left, puts the double bond at carbon number 1, as opposed to left to right, that puts the double bond at carbon number 3. So this would be known as 1-butene. The 1 is the location of where you find the double bond. And once again, if there was something else attached back here, it would be numbered accordingly based on the double bond taking the precedent. Any questions on that there? I was going to say, I think after all my sentences, because I think that's how you do it, but it sounds about right. All right, so we talked about our alkyl groups and really the need to lose a hydrogen to allow those guys to bond in without giving our carbon too many bonds. So these are our regular sort of normal groups, and they're all really based off of our methane, ethane, propane, butane, pentane, hexane. They're all basically missing 1 hydrogen to allow them to bond. All these guys are going to bond through the primary carbon. At the end is where these guys will bond. As we talked about earlier, you could classify the carbons as primary, secondary, tertiary, and that sometimes does bring up different types of groups. Very popular group, again, is the one we talked about before there, which is our isopropyl group, which is basically our CH3, CH, CH3 type of move, where the connectivity happens there at the secondary carbon. The IUPAC name you can see is a little bit different, but most people will use the common name for this one. Same thing here. This is actually an isobutyl group where it attaches at the end, but it still has like an isopropyl type of connection there. This is sec-butyl. The connection here happens at a secondary carbon, which is what the sec means there, and it's 4 carbons, which is from butane. And here is T-butyl, which means is tertiary, is really what that means. And that's because the connectivity here is happening at the tertiary carbon. So again, there's a lot of groups that have sort of historical names or common names that are still used today. And they're based sometimes on sort of where the connection is basically occurring. All right, so again, if we look at this guy here, longest carbon chain is 1, 2, 3, 4, 5, and 6, which means they're all single bonded. So the base of the name is hexane. This is the group that's attached that's not part of the longest carbon chain, and that is a 1 carbon group based off of methane. So it is now a methyl group. And we do want to number it, so you can probably see that if you go left to right, you are going to give that guy the smaller number, which would be in this case 2. So this would be 2-methyl hexane. Again, a reminder that between a number and a letter, you throw a dash, and between 2 numbers, if you throw a comma. So those are, again, common ways that we sort of number these things. Also, going from a letter to a number, you would dash it on the back end if you had that transition as well. All right. And this also demonstrates what we were talking about before. You do want to check all your options. Again, the longest carbon chain may not always be the straightest. In this case, we're coming down, and coming back up as our longest carbon chain. So sometimes it's really good to sort of try to check all your options and make sure you don't miss anything that may be correct or not. Here again is our numbering, and again with our alkanes, as I mentioned, it is the groups that take the priority. Once you get past alkanes, it's really the functional groups that take the priority there. Now, again, as we also saw in one of the examples I drew, if you do have more than one of the same group in the compound, again, they do not have to be on the same carbon or anything like that. We do use prefixes for those groups. So di would mean, like we had, I think, in the one I drew. You got 2, say, methyl groups would be dimethyl, or tri for 3, or tetra for 4. We do put the groups in alphabetical order regardless of prefix. So you do look at the actual group name, what letter it starts with, and it does go in alphabetical order regardless of prefix. Also regardless of numbers. So if you happen to have, say a 5-ethyl and a 2-methyl, once again, even though this has a bigger number, it is based on alphabetical E before M. So it does regardless of the number that's in front of there. It's just the actual prefix or the name of the group that you look at. And there's an example of this one. So if we were to name this one, once again, we got 1, 2, 3, 4, 5, 6 carbons, which means the base of our name is hexane. Here we would number going left to right, which gives us 1, 2, 3, 4, 5, 6. If we went the other way, 1, 2, 3, 4, 5, 6. And just so you're sure, if we go left to right, it is 2 and 3. If we go right to left, it is 4 and 5, and it is as simple as 2 is smaller than 4 is basically how you do that. If you have multiple numbers, if the first number is smaller, that's the way you go. So we obviously would go this way, and that again would give us a 2, 3, a dimethyl, and a hexane there at the end of it. Any questions on that there? All right. All right, so I think we did that one there. We just did that one, so it's good. All right, so why don't you try this one here? Give a name on this one. Okay, let's take a look. So there's a few different ways, but I believe the longest continuous carbon chain would actually just be straight across 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6, 7, and 8, if I could count. I think all other options end you with 7, which would be too short. That means that not part of the main chain here is we have this group, we have that group, and we have that group. That's basically not part of the main chain. But since we already know that the longest continuous carbon chain is 8 carbons, all single bonded, would be octane as the base of our name. We've seen our CH3 before, which is our methyl group. And this is our methyl group. And this is our ethyl group, which is a 2-carbon group, right? Based off of ethane. So we do want a number. So we got a couple of ways we can number here. We could go left to right, which is going to give us a 1, a 2, a 3, a 4, a 5, a 6, a 7, and 8. If we go right to left, that'll be a 1, 2, 3, 4, 5, 6, 7, and 8. All right, left to right, we have groups at 2, looks like 5 and 6. Going right to left, we have groups at 3, 4, and 7. So once again, it is as simple as that is a 2, and that seems smaller to me. So I'm going to go with that way. So we would actually want a number in this direction in this case. Any questions on that there? We also have 2 methyl groups in this case, right? Which means that we have a dimethyl situation going on. And in this case, that dimethyl would be at carbon number 2 and carbon number 6 in this case. We also then have an ethyl group, which is at carbon number 5. Now we're ready to put it in alphabetical order. Alphabetical order is E before M. So even though we do not look at the prefix here, so putting all this together, here we go. That's going to be a 5-ethyl. That then would be a 2,6 dimethyl. And a little octane action on the back end there. There you go. And then we're good in that case. Any questions on that there? What's that? So what in terms of the numbering, is that what you're asking? Yeah. So when you're naming alkanes, because they're all carbon-carbon single bonds, in terms of the numbering to get the lowest, it's actually the groups that are not part of the longest carbon chain that take the priority. So in this case, it's the methyl groups and the ethyl groups that take the priority in terms of numbering, as to which way you should number it. When you go to actually put them in naming order, it's alphabetical based on the group. And it's not the prefix part, but it's actually the start of the group name. So we're really looking at M versus E here in terms of alphabetical. So we would go with the E first, even though it has a larger number. It's alphabetical based on the group name, regardless if there's a prefix in there. So you ignore kind of the prefix of it. Right. If there was happened to be another thing there, like a propyl group or something hanging out there somewhere, then they would come after the methyl group. So it's all alphabetical, the groups, when you do alkanes. And any organic guide, the groups that are not part of the main chain are always put in alphabetical order, regardless of the prefix. The only difference is when you move away from alkanes is the numbering part of it. And the numbering part, once you move away from alkanes, any other sort of functional group past alkanes, it's always the functional group that takes the priority in terms of numbering. So, you know, like we did with the alcohol, whichever way gave the alcohol, the OH part, the smaller number was what took priority there. But because alkanes really only have carbon-carbon single bonds, some people even say they don't really have a functional group because it's all carbon-carbon single bonds. It's actually the groups that take the priority in numbering, but past there, it's actually the functional group part of the longest carbon chain that takes the priority in terms of numbering. We will not in this class. I just did that as an example to kind of show you that once you go past alkanes, we could if you want, but you don't have to worry about it. But unless you take organic, then you have to worry about it. But yeah, so so for us, we're going to kind of stick to alkanes in here. It's just kind of a survey of organic to, you know, entice you to go to the Chem 80 all excited. Okay, let's take a look at some of these here. We'll start at the top one. So if we just go straight across, sometimes easier just to see how many carbons. So that was 1, 2, 3, 4, 5, and 6. We also could go 1, 2, 3, 4, 5, which is a little short. 1, 2, 3, 4, 5, 6. That's 6 as well, actually. We then could also have gone 1, 2, 3, 4, 5, 6. So looks like there's multiple ways you could get to 6. My recommendation is if there's a kind of just a straight old way there to get to 6, might as well go with that one. Makes sometimes easier to see everybody else. So we'll go with the 6 that's just straight across here. So that 6 is going to be the main part of the group or the chain. That means we have these couple groups hanging off of it. So to construct our name, 6 all single bonded is going to be hexane. This is a methyl group. That is a 2-carbon group, which is a ethyl group based off of ethane. And perhaps you could see it, but if you go right to left in this case, 1, 2, 3, 4, 5, and 6, that will give you a group here at carbon number 2 and 4, as opposed to 3 and 5 if you went the other way. So that is the way we would want to go. That means our methyl is at carbon number 2, our ethyl is at carbon number 4. And again, it's going to be alphabetical here. So we're going to go with the E before the M. And this would be a 4-ethyl, a 2- can barely see it, methyl, and a hexane there at the end. Any questions on that name there? Taking a look at the guy on the bottom left there, I think is pretty straightforward here. We'll go 1, 2, 3, 4, 5, 6, 7 carbons. I think that is the most that you got going on there. In this case, we then would have just a methyl group hanging out. And here, 7 carbons means that the base of the name should be heptane, as they're all single bonded. We have our methyl group here, and we would want to go perhaps 1, 2, 3. If we go the other way, 1, 2, 3, 4, 5. So we definitely would want a number in that direction. And that would be a 3-methyl heptane. Any question on that one there? Yeah.
Okay, what if the equal group is on 5 instead of 4? How would you name it? Like 5 instead of 4?
You would not, because then it would actually become, so your question is if you kind of shifted that group over 1 carbon. So let me just kind of redraw it real quick here. That's 4, 5, and 6. And if you move that guy from carbon over here, I'm just going to draw the carbons without the hydrogens. So what that would actually do is now you would have the longest carbon chain being this guy, right? Which would be 1, 2, 3, 4, 5, 6, and 7. And you would have these guys as methyl groups as guys are attached. Yeah. Yeah, so you'd have a little dimethyl, whatever many carbons we had there. 1, 2, 3, 4, 5, 6, 7, 8. So 3, 6, 7. So you would have something like 2, 5-dimethyl heptane. It would become. Yeah. And obviously that happens because that's a carbon. So now it actually adds to being the longest carbon group. Other questions? All right, so if we look at this one here, if we go straight across, that is 1, 2, 3, 4, 5, and 6. If we start up here on top, 1, 2, 3, 4, 5, 6, 7. It's not too bad. If we maybe start on top and go 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, and 8. If you go that way, and I think that's going to be a winner on that one. So in this case, the longest carbon chain, as you could perhaps see there, is not the straightest, but it actually should be running through here, 1, 2, 3, 4, 5, up 6, 7, and 8. So that is going to be our longest carbon chain, I believe. That means that we got a couple groups, which is actually this group here and this group here, which is our methyl and ethyl group. So based off of that, and again, that illustrates that you do want to kind of check all your options because you never know where that kind of longest one's hiding. We have the ethyl, and we have a methyl, and we have octane as the base of our name. Now, numbering wise, if we go to the top here, 1, 2, 3, 4, 5, 6, 7, and 8, that would put groups at carbon number 3 and 5. If we numbered the other way, starting with 1 over here, 2, 3, 4, 5, 6, 7, and 8, that would pick groups at carbon number 4 and 6. So we definitely want to go the 3 to 5 route, which was our first numbering arrangement, I believe. So we'll go this way. All right, so again, going alphabetical here. We're going to do the ethyl first, which is actually number 5. So that's going to be, if I get something to write with here, it will be something. There it is, 5 ethyl, 3 methyl. I'm going to try to join it up here, octane. Any questions on any of those examples there? Is fun with naming. All right, let's try a couple of line structures just to, make sure we know how to do that. So I'm just going to draw some random stuff. And, maybe it will work out. That looks good. Let's do this. Let's do this. Let's do this. Why don't we also do a little bit of this action here? And let us do a square because everybody likes a square, even though it kind of looks rectangulish. All right, give it a go. See what you come up with here. Hopefully it's something, not just squiggly lines. It could just be squiggly lines. Yeah, figure out the name of these guys. A reminder that if it's in a ring structure like I talked about earlier, it becomes cyclo in front of the alkane name. Yeah. All right, let's take a look here. So look at the top left there. I think you could roll just straight around 1, 2, 3, 4, 5, 6, and 7. I think you'd also get 7 if you started here and came up and went to the right. So it does look like 7 is perhaps the longest continuous carbon chain here. That means we would have this group here, and we would also have this group hanging off of there. So starting with the 7 means they're all single bonded there. So that is heptane as the base of our name. That is going to be named like we did with our sort of complex ions. So that is bromol. This is a 1 and 2 carbon group hanging off of there, which is an ethyl group. At this point, you could probably see that if you number right to left, it's going to give that bromine a 2 for a number, as opposed to if you went to left to right, you would hit a 3 when you got to the ethyl group. So we would probably want to number this way: 1, 2, 3, 4, 5, 6, and 7. And in this case here, that would then give us alphabetically B first. So that would be 2 bromol dash 5 ethyl, and then a little heptane action there at the end. Any questions on that name there? All right, take a look at the guy at the bottom there. 1, 2, 3, 4, 5, 6, 7, 8. I think you could also get 8 again if you started here. 1, 2, 3, 4, 5, 6, 7, 8. Kind of coming across there. So we'll go with 8, which looks like the longest. As I made the extension there, that leaves us this lonely line there and a second lonely line over there. So 8 is going to be our octane as the base of the name. Remember that lonely lines and line structure are methyl groups. They are basically at the end of the line of carbon that should have 3 hydrogens attached. So both of those lines there would be a methyl. And if they wanted something there, they would definitely put it there if they did. In this case, you could also probably just visually see going left to right here is going to give us the smaller numbers. Obviously, going in the other direction, you will end up with larger numbers. So this is a 2-methyl in the same compound. So that is going to be a dimethyl situation. And it's going to be a 2,4 dimethyl. So this would be 2,4 dash dimethyl for the location of those methyl groups. And then we would finish it out with our octane. Yeah. Any questions on that there? It is. So B would come before E. Yeah. So it's not really a functional. Well, I'll put it this way. Some will consider a functional group. They'll consider it, like we saw in that table, as like an alkyl halide, which is sort of a class of organic groups that are basically alkanes that have a halogen on it. So they do sort of consider it sort of like a functional group, but it's not necessarily in this case truly a functional group. It's just sort of a group that's attached. And the halogens are all like that: fluoro, chloro, bromo, and iodo. It is sort of a class of organic compounds, but not maybe traditionally like a true sort of functional group, but some will sort of consider it. So we wouldn't necessarily give it the priority, but we would still want to go whichever way has the smaller number. Other questions? So here we got a little cyclic action happening. These are all single bonded, which means definitely the longest carbon chain is our ring here. And that ring is, we're going to do the same thing, just count up carbons. So that is 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons, which is hexane. Because it is in a ring, we put the cyclohexane part of it in there. So that is sort of where the cyclo comes from. In this case, we have just one group attached, which is a bromine. So this would be known as bromocyclohexane. Now you may be asking, do you have to give a number? In this case, you do not, because it's only one group attached to the ring. Wherever that group is would be carbon number 1. So if you move that Br group to the carbon below it, it would still be the same, and it would be carbon number 1 because it's what is referred to as being mono-substituted, just one group attached, basically. Now, when we come to the guy on the bottom, though, we still have the ring here as our longest continuous carbon chain, and that would be 4 carbons there. 1, 2, 3, and 4. So 4 carbons would be butane. Again, it's a ring structure, so it becomes cyclobutane. And now we have this group here, which is a lonely line, which is a methyl group. And we have this guy, which is a bromol group. In this case, we actually have 2 different groups that are attached, or 2 groups that are attached, really, to this. In this case, we do need to give numbers. So we do need to give the location of these guys. Now, in this case, because we're going to put the groups in alphabetical order, we should start numbering out which one would make more sense. Yeah, so we would call this number 1. And then we could go clockwise or counterclockwise. In this case, we'll go up to 2. Obviously, we went the other way, it would be 4, which would be a bigger number. So this would be a 1 bromol, 2 methyl. I'll try to squeeze it in there. Cyclobutane. There you go. Got it. Any cool? Yeah. So in this case, where 2 things could happen when you're numbering in an alkane or in any situation, but You could have a situation where the group is sort of equally numbered, no matter which way you go. So if you went right to left, it's like 1 and 2, or if you went left to right, it's 1 and 2, and those groups end up on the same sort of carbons. In that case, what you would then default to is you would want to go whichever way is more alphabetical. So in this case, we could have started numbering at either group, but really, since you're going to put the groups in alphabetical, that would sort of take the priority. You would want to give the alphabetical guy the smaller number in this case, would be the more appropriate thing to do. Yeah. And that does sometimes happen. You do sometimes get like a tie in numbering, like you go either way and it's like the same numbers no matter which way you go. And in that case, you would also then default to whichever way would probably give the smaller number to the more alphabetical guy that would be there. Other questions? Questions on naming these alkanes? Fun. All right. So let's just finish up by actually talking about how to go the other way. If you actually have the name and you want to draw the structure from the name. The good news is if you come to this part, it's actually, frankly, the easiest of it all, because basically it tells you what to draw. So the key when you're drawing something and you have the name is, frankly, you should always work in pretty much all cases backwards. So you should always work backwards on the name. So if we look at this first one, which is 2,3-dimethylbutane, butane tells us that it is 4 carbons. So that's frankly all I'm going to start with. No hydrogens, just going to start with sometimes called the carbon skeleton. Those 4 carbons take care of the butane part. I now have 2,3-dimethyl. Dimethyl means I have a methyl group, and di means I have 2 of them, and they're at carbons number 2 and 3. The beauty is, since you are drawing it, you can number left to right or right to left. It doesn't matter. So I'm going to go left to right. So for me, I'm going to call this carbon number 1, but you could have called the guy on the right carbon number 1 as well. So for me, carbon number 1's there, which means at carbon number 2, which would be there should be a methyl. And at carbon number 3, which would be there should be a methyl. That takes care of that. That takes care of that. I am pretty much out of name at this point. What is left is hydrogen. And we put enough hydrogen so that carbon ends up with the magical number of 4 bonds. So the carbon on the far right has 1 bond going in, so he needs 3 hydrogens. The carbon next to it has 3 lines, which means it has 3 bonds. It needs 1 hydrogen to get the 4. Guy next to it has 3 lines, needs 1 hydrogen to get the 4. And the first guy over here needs 3 hydrogens to get the 4. And now I have my structure there. Now, if I, first off, any questions on that there? If I wanted to do line structure, you would do the same. You would just start with the 4 mountain range, yeah? And you basically would do the same thing. You would go whichever way you want to call number 1. So I'll call this number 1 for me. And again, you would do the same thing. You go carbon number 2, which would be here, and you draw a methyl, which is just a line. And you would go to carbon number 3 and draw a line, which is a methyl. And in this case, because it's line structure, you don't have to worry about filling in the hydrogens. They're assumed to be there, and you're done in that case. Yeah. Any questions on that? So why don't you try the bottom 2 there? Draw up the structures, both the condensed structure and the line structure. So heptane tells us 7. Ouch, 7. 1, 2, 3, 4, 5, 6, and 7. That takes care of that. Again, 3, carbon number 3, we have an ethyl group, and carbon number 2, we have a methyl group. So once again, for me, I'm going to call that guy over here carbon number 1, which means for me at carbon number 3, there's an ethyl group, which is a 2 carbon group. And at carbon number 2, there is a methyl group, which is a 1 carbon group. And once again, at this point, everything else is going to be hydrogen to get to 4. So that would be 3 for that guy. This guy has 2 lines coming in, so he needs 2 hydrogens. 2 lines needs 2. 2 lines needs 2 hydrogens to get to 4. This guy's got 3 lines, which means he just needs 1. This one also has 3 lines, just needs 1. And this one just needs 3. Any questions on that one? Again, line structure here, we would start with our 7. So 1, 2, 3, 4, 5, 6, and 7. Again, I'm going to go left to right. So the guy over here is going to be carbon number 1 for me. That means, again, a carbon number 3, there's an ethyl group. So I'm going to draw it up since I'm kind of running into writing on the bottom there. And a carbon number 2 would be a methyl group. So it looks something like that in that case. Or if you drew that ethyl down the bottom, it would look fine as well. Any questions on that there? Lastly, here we have pentane. So working backwards, pentane is less carbons. Thank goodness. So that is going to be 5, I think. That takes care of that. Again, I'm going to go left to right, calling that number 1. So at carbon number 4, which would be down here, we have a methyl group. And a carbon number 2, which for me would be here. We have a chlorine group. And again, we're going to fill in our hydrogens. This guy needs 3. This guy needs 1. This guy needs 2. This guy needs 1. And this guy needs 3. Again, the goal is to get carbon to 4 bonds. If you did your line structure, you would start with 5 in a line structure situation. 1, 2, 3, 4, 5. I call on this number 1 again. We would go to carbon number 4, 1, 2, 3, 4, and draw our methyl group straight up. And at carbon number 2, we would have our chloral group, which we do need to put the Cl at the end of the line to indicate that it is chlorine. Yep. Any question on drawing them? Yeah. It really doesn't in an alkane. So one thing you'll learn when you go to organic, if you do, the single bond actually has freedom of rotation. So it could actually freely rotate around the bond. So any group could be up or down. When you actually get into alkenes and alkynes, the double bond or triple bond, it actually locks everybody into place. And it creates actually isomers where groups are kind of locked at either on one side of the double bond or the other. They lose the free rotation around the carbon-carbon bond. So in the case of this, usually it's okay if you draw it up, down. It doesn't really matter which way you kind of draw it. Yeah. Other questions? Questions on organic? This was fun. Good times.